Hi and welcome everyone to Mackie Academy YouTube channel. Today I'm going to continue the lesson by looking at one example, a simple example for combined loadings. Here we have, as you can see on the screen right now, a system that we call force couple system. This is a force couple system, and typically, right, for combined loadings, the questions usually interested in to know what is the stress element at, for example, in this example, K and H, where the 2 points apart is 90 degree from each other. So by taking this a three-dimensional x, y, z as a Cartesian chart for this L bracket in here, and next I'm going to list down the dimensions involved for this example. The distance from the base to the tip of the L bracket is the distance here to here is in meter, 0.5 meter. You can see that the distance of the tip of the L bracket. Just not happy with this. To erase this and rewrite it again. This is right, the distance of 0.15 meter, and from point K to the center of the beam of the shaft is 0.2 meter, take as 0.2 meter, and we have two point loads. The point loads going to create force couple because of the distance and the force and the distance. Here we have 7.5 kilonewton, that is one, and another one is pointing downward. This is the magnitude of 18 kilonewton. So this is the system that we have for combined loadings. This is under, if I can specifically would like to create this video for combined loadings revision. This is in fact the revision of 3D combined loadings. This is 3D revision for 3D combined loadings. This is the last part in the syllabus for Solid Mechanics 1 according to Hiveler's textbook. Perhaps all the information that you gathered in Solid Mechanics 1 is in this chapter. The transition to Solid Mechanics 2, part 2 of Mechanics of Material, we're going to begin with this. Knowing how to solve combined loadings, how to get the RVE, the so-called stress element. In 3 dimension we call it representative volumetric element. At a certain point is going to help you in solving further in this later part after combined loading. This is the first chapter for Solid Mechanics 2. We have stress transformation, but first of all we need to compute correctly the stress element at both points through K and H. And here I'm just would like to show the solution. First of all, I'm going to begin with point H. Whatever the Cartesian chart system that we have in here. So first of all, we're going to have a look on the listing down the point loads, and typically we can say this system is equivalent to, if you want to break it down into free body diagrams, a so-called simplification before we do any before we attempt to solve any of the structure problem. Going to come up with the list of the forces, direction forces acting on the structure. Here we have at both points we have this is at point K, and a 90 degree to this, right? 90 degree to this. This is point H, where the questions that we try to attempt to solve. And by looking at this system that we have, this is y vertical, we have y vertical, positive y, we have I'm going to put it in here. This is P, the point load of 18, right? Point load, and I'm going to have a double tip arrow to represent the torque that we have due to P. If you can list down in here, this is P 18 kilonewton, and we have T, yeah, this is T with a double tip arrow, T equivalent to the 7.5 kilonewton times by the arm, or the distance between, according to the diagram, this is 0.15 meter, and it comes out to 1.125 kilonewton. I hope you can see that this is the if you guys do the revision before your exam, test or exam for combined loadings, right? This is the skill, looking at three-dimensional. It is not straightforward, but being able to see this going to help we're going to help you a lot in solving this type of question. This is point K, this is point H, and we're going to list down there are at least three more reactions that I'm going to from the direction of x. We have moment x acting at point K. This moment x due to the rotation of 7.5 going to create right, this 7.5 point load with a distance of 0.2 are going to make again at the moment like similar with the talk previously, but this is from this view we call the moment acting at that point, because the rotation, you can follow the right hand rule. So from this view that I'm going to put it, this is moment x. By the way, moment and torque, the magnitude, the unit for both terms are the same. We have moment x on that direction. We have last but not least on z direction, we have shearing occurs, which is coming from 7.5 kilonewton. We have on this direction, we're going to have V on z direction, that is 1, and last but not least we're going to denote this as a double tip arrow. Again, this is moment z due to 18 kilonewton rotating the double tip arrow is just the representation of a right hand rule. The arrow is just this way if you like, but to simplify the thing, to not make it crowded, this is moment z acting on that way. And the next thing I'm going to do is to list down that we have P equivalent to 18 kilonewton, T already done, V, the shear force is just 7.5 kilonewton. That is the magnitude of shear force for this system. We have moment x that I said earlier, the magnitude is 7.5 multiplied by 0.2, the distance is equivalent to 1.5 kilonewton meter, and we have moment z direction, positive z direction, pointing to and the this moment z was caused due to 18 kilonewton the point load and the distance of 0.15 meter as shown in the figure, and we have here 2.7 kilo Newton meter. So we have all reaction forces and coupled system listed in this part here, and it is now a lot easier for us to compute the rest of these stresses, because this question in here, they would like to see the goal, if I may say, for this question, find the RVE for H and K. But what I'm going to do now is to try to attempt first of all point H, how to get the looking at the structure that we have, the system that we have, looking at from the top view, we have this. It is easier to see if I can make it a circle like that. We have point K over here, and this is point H, right? And this is the cross-sectional area looking at the top, looking from the top of the structure, and I draw that diagram for us to see clearly that we are going to involve all the stresses that we discussed in the previous video, right? 4 types of them, divided into 2 types: sigma for normal stresses, and the other one is tau for shear. The shear going to be divided into 2. One is in torsional type, and the other one is the transfer shear. And if you can remember, the transfer shear, the system is not that straightforward. We need to know all the terms involved. For example, the first moment of area denoted by a capital Q. So I'm just going to do just that, to make to break it down into computable terms when we it is easier for us to use it when I list down the equation for each of the stresses. So the radius, if I haven't give you the radius for this question here, yeah, I haven't done that. So the radius for the shaft, for the force coupled system, take radius, because this is take the similar radius for the system. This is equivalent to 0.03 meter, right? And then when we have that r equivalent to 0.03 meter, next we can calculate the area, which is pi r square, and you can compute this, right? And it comes to the area for this shaft over here is 2.8274 times to the power of -3 10 to the power of -3 square meters. And next, the moment of inertia or second moment of area. Don't forget the formula for this. This is pi r to the power of 4 over 4, right? We discussed this in the introduction of this revision. We have pi times to the power of 0.3 again to the radius, but now to the power of 4 divided by 4. So we have the value for I is 0.6362 times to the power of 10 to the power of -6 meter to the power of 4. J, the polar moment of inertia, will be needed as well, and we can calculate that by using pi r to the power of 4/2, or you can say this is just 2i if you like. This is just a simplification, but you can go ahead and plugging the value in the radius, just put it in your calculator, or you can simply multiply I by 2 when you have 1 point, the double of that value. This is 1.2723 times to the power of 10 -6 meter for the magnitude I and J is the same. Now this is the part that which is, it is interesting. This is Q. Q for a shaft for a circular shape, a cross-sectional area. We have 2/3 r to the power of 3. So if you, this is the simplification of this. This is 2/3 times by 0.03 to the power of 3 equals to 18 times to the power of 10 -6 meter cube. And in our case, I discussed this briefly. T is the thickness of the shaft, whatever prismatic beam that we have. T at the moment is equivalent to double of the radius that we have. So this is just 2 times by 0.03 the radius. It comes to 0.06 meter. So this is this section over here. We are looking at all the terms that we're going to use in the next solution, and I think my emphasis is I just want you to focus on this. You want to focus on the maximum. If you still remember, Q, the maximum will be for rectangular shaft, going to be in the middle, and the shape is parabolic. Q, how do we compute Q? Q is just the formula is A prime times by y bar prime. Y bar we understand. Y bar is just the centroid of that shape, the distance of that centroid to the middle, which is what we call the natural axis. But for Q, the distance now the prime representing the same concept with the centroid, but Q now it depends on whether it is above or below. We don't have that case above and below for shaft, because the area, if you can see at the top and the bottom of this circle, they are equidistant. The amount is the same, and the Q, we know the stress for transfer shear, the profile of transfer shear are going to be parabolic, just like that. But the maximum Q, we have the problem when we have this shape of a circle. So in this solution, I'm going to use 2/3 r cube is the formula for circle. You can Google or take a look on Wikipedia on how Q is computed for a circle. For a circle, or in our case, we have a half of the circle. Now, having said that, we listed down all the terms that will be required, and I'm going to move and try to solve for this. Is the point H that we trying to come out with the stress element. So we have at point H focusing exactly, this is exactly on this point, at this point here, right, or this point here. This will require your imagination, so focus on that. We have for point H, we don't have a sigma x whatsoever, because there is no looking at the system again, we don't have any point load acting on x direction, because there are only two point load that we have, 7.5 kilonewton directing toward along z axis, and another one is 18 kilonewton, and simply said there is no element that create the stress on the normal stress, to be exact, on x axis. So I hope you that will be understood by now. This is the second part of solid mechanics, and I'm going to go ahead with this is sigma y for the system, which is we know this before. This is my over I for bending, due to the bending, and in this case I'm going to say this is moment x times by the radius. We don't have y for a circle, just I'm going to replace this as a y as r radius is the outermost radius that is complementing the, if you see, remember this is the equation my over I for bending stress, and divided by I, the moment of inertia. And in our case we have opposite direction of p, and I'm going to minus that with the normal stress p over a. So I hope you can see that how to make it simple for you to understand. For y, on y direction we have on y direction we have 18 kilonewton acting downward. There is one direction. If in combined loadings, whatever is opposite to that direction, you can do not the magnitude, the sum of the stress is going to be done accordingly. Bending moment at point H, right? I'm going to emphasize this is we are looking at point H at the moment. 18 kilonewton is pushing the point H downward. The normal stress going to compress, if you like, right, the point H downward. And there is another element of stress. In this case we have moment x, right? Moment x, if you look at the, is trying to resist that the normal stress upward, and the result is the we need to minus that, and I'm going to begin with the positive for that direction, moment x times by r over I, and because p is pointing downward is usually affiliated with the negative, and so we have minus p over a for that particular location. So go ahead, and what you need to do is just plug the value in this equation to make it, this is 1500 times by the radius, right, 0.03, and the I for we already solved this earlier, 0.6362 times by 10 to the power of negative 6 minus 80 kilonewton, and the A 2.827 times by 10 to the power of negative 3. So simplify this, you gonna get 70.74 times 10 to the power of 6 minus 6.37 times to the power 10 of to the power of 6. These are comes to 64.37 in megapascal unit, most typical unit for structural analysis if we are working on metallic material. Should have in the unit of megapascal, and we also have tau for this system. We have tau xy, we have the tau. In this case we have torsion. The formula for torsion is Tr divided by J, right? So T, we already discussed this earlier. Over here, look at this. T is the value for torsion for our system. So at point H, it's going to be caused by that 11.2. This is 1.125. If you want to, we need to compute this, and taking that 1.125, 1.125 times by, that is in kilonewton, right? This is in kilonewton, times by 0.03 divided by 1.27. Everything is in SI unit that I'm trying to do over here, and it's supposed to be to come to 26.53 megapascal. This is the value for the torsion at the location H, right? So that is we solve all. Is there anything else that we miss at point H? A torsion is due to the top that we have 7.5 times by 0.15, the distance. That is the top for and it is acting at point H as well as point K, if you like, but we are focusing at one point right now, point H. So 1.125 kilonewton. This is what we have before, and we need to according to torsion formula, right? Tr over J, just plug and chug, and you have that 26.53, the value for shear stress. Even though it is caused by torsional, there are two types of shear. One is torsion, another one is the transfer shear. That is point H. That and probably you need to the goal for this. You need to draw. Typically in the questions they ask you to write down in stress element, in the representation of the we call this RVE for point H, right? Just draw a box like so. This is x direction, right? This is x direction, and in our case we have two stresses. This is simple. This is the positive sign for shear stress on the stress element. The value is just 26.53, right? This is megapascal. And what about the on y direction? We have sigma y just now, the equivalent to 64.4, which is on this direction. The positive direction for this is actually the sigma 64.37 megapascal. So we have done that for point H in this solution, and probably want to go ahead and compute the same thing. This is the revision for 3D combined loadings. After this, we're going to do starting from the stress element over here that we already computed. This is a rather a simple example, but it will take so long to discuss. I really like to focus on the 3D combined loadings, and what we have over here is the RVE. Starting from here, you can use a Morse circle to solve for principal stresses and maximum in-plane shear stress. That this is going to be on the next chapter, right? Perhaps that is the I would say this is the first chapter for part 2 of solid mechanics. And apart from Morse circle, the solution also true if you use a Morse circle is a set of equation, and perhaps you also going to know how to use the graph paper. This is analytical method, and this is the graphical method. Graphical method. Probably you can use the graph paper plus a graphical method, where you need to use the compass and the protractor in order to solve for the same thing. And at least there are two solutions that are really popular in solving for the principal stresses at particular location. In this case, we solve for H. If you want to go ahead and solve for the point K, which I didn't do over here, so probably I'm going to give you just the RVE, so that you can probably try to attempt. This is for point K, which is another point mentioned, drawn on the original question, and this is just the solution. I'm giving you the solution for this. This is again positive for shear stresses to the magnitude of 30.06. This is x direction on y direction, and now this is downward. We're going to have negative value for this, and the value for sigma y, if you take for point K, will be make sure you get this value. The arrow itself going to show you the direction. Actually, you should have negative, or probably it is easier for you, because I don't have to put negative value, because the arrow itself pointing downward, representing the compressive behavior at point K due to the normal stress on y direction. Or probably bear in mind that you're going to have a negative negative 133.69 megapascal for your solution, just to make sure that that is the value that you can have for point K. So from here, right, this is the revision for 3D combined loadings, and on the next we're going to recall a few methods I mentioned there already: Morse circle, graphical method using protractor, and the graph paper with your graph paper. You will need them to include the location on Cartesian chart on 2-dimensional. But apart from Morse circle, Morse circle, of course, going to, in order to create the circle, you need to have your protractor and compass. But if you a Morse circle per se, you have a specific solution for that. We're going to learn on the next part of the video. Graphical method is exactly by using, if you can recall, a graphical method is just the vector method. If you draw correctly with the right magnitude for each boxes, each of the box representing the magnitude of the force, and you can simply compute the resultant force, for example. So I think with that I'm going to end this this video for revision for 3D combined loadings. Stay tuned and see ya in the next video. Thank you very much.